All right, so we're going to take a look at one quick example for determining average energy for a monatomic gas. So there's a couple of things that you need to know. One is that the system partition function is related to what's called the molecular partition function with this formula right here. Okay, so Q is the system partition function, and little q is the molecular partition function. So the reason why we like molecular partition functions is because we can calculate them pretty easily. All right, and this one is 2 pi m over h squared beta to the 3 halves times v. Okay, now how do we calculate this? We calculate this from the energies associated with a particle in a one-dimensional box. I'm not going to go through that at this point, but this can be done. This is nice because we know the molecular energies, right? So if we go back to what the partition function is, there's an energetic term in there. And we know what those energies are for a molecule. And I'll get to this. We're going to deal a little bit more with this as we move through this lecture. Okay, so this is for an ideal monatomic gas. So think helium, argon, that kind of stuff. And I'm going to move so that get rid of that glare. Okay, there we go, kind of away from the glare. All right, so we said in last lecture that the average energy is negative partial of ln of q with respect to beta, holding n and v constant, right? Now q, big Q, is a function of little q, according to this. So if you remember your logarithm rules, let me write this out. We've got negative partial with respect to beta. Okay, the natural log of big Q is equal to n times the natural log of little q minus ln of n factorial. So we've got that. And we get this from, like I said, the logarithm rules. So remember that if you have the log of a to the n, this equals n log of a. And then the other rule is if I have ln of a over b, that equals ln of a minus ln of b. So we kind of put both of those together in deriving this. Okay, so the reason why we want to do this is because it makes the math a little bit easier. So now if we want to calculate the average energy, we need to take two derivatives, one of this thing and the other of this, right? So if I plug in what Q is, so remember Q is this stuff right here. So we're going to take that, Q, and we're going to plug it in here. Okay, and in doing so, we're going to wind up with, so the average energy is equal to negative partial with respect to beta. We're not yet ready to take the derivative. Okay, negative There's no negative sign there, I don't think. So 3 halves n times the natural log of beta plus n times the natural log of 2 pi m over h squared beta to the 3 halves v minus ln of n factorial. I'm going to take the derivative of all this stuff right here. Oh, sorry, there is a negative sign here. There is a negative sign because beta is downstairs. It's in the denominator. So, okay, so how do we get this? Same thing. We've got ln of a over b is ln of a minus ln of b. We're grouping all of this stuff into a, which is 2 pi m over h bar, or h squared to the 3 halves times v. That's 2 pi m over h. This beta doesn't belong. 2 pi m over h squared 3 halves v. Right. So that's a minus b, which is beta. Okay. And then I also took the 3 halves and put it out front here. We don't have to do that here. It doesn't matter. The reason why I'm doing this is for the following. We're taking the derivative with respect to beta. There it is. There's beta. All right. If you notice, in all this other stuff, there's no beta. Oh. That means that when I take the derivative of it, the derivative of a constant is 0. So those terms, that's 0, and I have a much easier time with the calculus. Okay? So, average energy is equal to, at this point, we're going to take the derivative of this. Okay? So, pull out my constant stuff. So I'm going to get 3 halves n. And then let's go ahead and write out the partial derivative. So I got the partial derivative of the natural log of beta over beta. The partial derivative of the natural log of beta with respect to beta. All right, let me just make sure that we can see what we're doing here. Let's say that y equals the natural log of x. If I want to do dy dx, that would be 1 over x, right? We said that last lecture. Well, isn't the natural log of x y? So if I put that in the numerator, then I would have d natural log of x dx equals 1 over x. So this stuff right here is just 1 over beta. So the average energy then is 3n over 2 beta. All right, now up until this point, beta has been some mysterious constant or something, or variable. Let me just go ahead and give you the definition of it. Beta is 1 over kt, where k is Boltzmann's constant. So the average energy is 3 halves nkt, or if we put this in terms of moles, 3 halves nRT, where I can express either number of atoms times Boltzmann's constant or number of moles times the universal gas constant. So those are the same because nk equals little nr. Those are the same. Okay, so this is a nice, nice way to get to something like average energy. You can also calculate pressures. You can do all kinds of stuff with the partition function. But before we do anything else with that, let's take a look at the relationship of the partition function Q with the molecular partition function. Okay, so there's actually two different things we need to work on. One is independent distinguishable particles. You can think about this as like atoms or molecules or something like that. And so think crystalline lattice. Okay, so independent means each particle, each atom, each molecule, whatever, is independent of the others. Distinguishable means that you can tell the difference, at least in principle, between, among them. All right. The reason for this is like if you have a crystalline lattice, let's say you've got a crystalline lattice where you've got all these atoms like this, and they're kind of packed together, something like that. You could, in principle, because they don't move around, they just stay put. You could label that one like row 1, column 1. This could be row 1, column 2, 1, 3, and so on, right? This would be row 2, column 1, 2, 3, 4, 5, right? So each one of these is distinguishable in principle from the others simply based on its location, even though they would all be, say, for example, iron atoms or carbon atoms or whatever the solid is. Okay, so for this kind of system, the partition function, Q, is related to the molecular partition function as Q to the N. And the reason for this is because Q is a summation, right? Let's just go back to that. Q is a summation. The summation of e to the minus beta ej. Okay, where capital EJ is the system energy. Well, the system energy is simply the sum of all the little energies. So like E1 plus E2 plus E3 and so on, right? So I have all these little energy of particle 1 plus the energy of particle 2 plus and so on, right? So because of that, I can shove all that in here, and I get that Q is equal to the summation. And then here we're going to look at summing over these different indices, I, J, and so on, of e to the minus beta, and then here I'm going to have EI plus EJ plus, and so on. Okay, so what are we summing over? These are all the molecular energies of, like, say, for example, this atom. These are all the molecular energies of this atom. And so on, right? So each one of these. So we're adding up all the molecular energies, which gives us the total energy, and we're just going to substitute that in. But we don't just add up the energies of each here in this summation. Remember, this partition function is a summation over all energies, not just one energy state. So when I do that, I can write this as Q is equal to the summation, and then I've got my indices, I, J, and so on. Right? And then we can, instead of adding these, we can take the products. E to the minus beta EI. E to the minus beta EJ. And so on. All right, now these are all independent. Let's go back here. Independent, which means I sum over each one of these indices independently of each other. This is a J. So when I do that, what this turns into is a product. And we can write out a molecular partition function, little q, as the summation of e to the minus beta EI. That's the molecular, it's the molecular energies, so it's the molecular partition function. And this comes out to be the product of all of those. Which is just q to the n. The reason why it's q to the n is because these are all the same type of atom, right? So it's all iron. Now, if you have an alloy or something where you've got like, you know, two different metals mixed together, then there are different energies. You have to worry about that. But this is just for a, you know, pure substance, right? So independent, indistinguishable particles of the same substance. All right. So for independent, indistinguishable molecules, we've got a little more work to do. Okay, so of course the total energy is the same thing. I'm just going to add up all of the molecular energies, right? All the energies of each of these. Oh, and this is, let me just write this down. This is independent indistinguishable. So not distinguishable. Remember, this one was distinguishable. Here, this is indistinguishable. They're not distinguishable amongst each other. Okay. So the partition function Q is equal to e to the minus beta EI plus EJ plus, and so on, right? Okay, now at this point we have to consider the summation, okay? And that is, we wind up with overcounting, okay? So we've got an overcounting problem. In this summation, if I have E1 plus E2, this is the same as E2 plus E1. That may be obvious. Not a problem over here. Why is it not a problem for independent distinguishable particles? Well, because the particles are distinguishable. So there is no overcounting. If this one has energy, you know, energy state 2 and this one has energy state 1, that's different than this one having energy state 2 and that one having energy state 1, because they're in different locations. But these are indistinguishable particles. So that means that these represent the same state. And this is a problem for both fermions and bosons. So fermions, this is like electrons. E1 and a plus E1 is not allowed. That is, two fermions can't have the same energies at the same time, right? They can't have the same state. So two electrons have to be in different quantum states. For bosons, so bosons would be like, photons are bosons. The Higgs boson, that's a boson. But they follow, so fermions follow Fermi-Dirac statistics, which is what gives you this. So fermions obey the Pauli exclusion principle. Bosons, no, they don't have that restriction, but they have the same kind of problem. For example, E1 plus E2 plus E2 is same as E2 plus E1 plus E2, right? So you still have the same kind of problem. Start overcounting. So how do we deal with this overcounting? We can correct for it by dividing by n factorial. And so this corrects for the overcounting, but there are some other terms in the summation with the same energies. So let's look at a quick example, just so that we can kind of get an idea of this. Let's consider a two-particle system, two fermions. Okay. And then we're going to have an unrestricted summation. Okay, so if these two fermions only have two states, okay, let's consider the simplest example. Two states. Okay, in the unrestricted summation, I'm going to have four terms. I'm going to have E1 plus E1, E1 plus E2, E2 plus E1, and E2 plus E2, right? All right, now if I look at this, how many of these terms are not allowed? Well, this one's not allowed, and this one's not allowed. These two are taken care of by dividing by n factorial, right? Okay, so that's with two states. Well, what if I had 10 states? How many terms are in the summation? Well, we can kind of think about this as like, if we kind of make a grid. 1, 2, 3, 4, all the way up to 10. Right? How many terms are there? Well, 1, 2, 3. There's 100 terms. Right? There would be 100 terms in the summation. So how many of those terms are not allowed? Well, there's 10 of them, right? If we go down the diagonal, that's where we get the E1 plus E1, E2 plus E2, E3 plus E3. Okay, so let's take a look. Let's kind of chart this up. So we got number of states. We've got the number of terms in the summation. And then we have the number of E1 plus, EI plus EI, where the two indices are the same. Okay, so if we have 2 states, we have 4 terms, and we have 2 problem terms, right? Well, if we have 10 states, we have 100 terms, and 10 of those terms are these problem terms. What if we have 100 states? Well, then we've got 10 to the 4 terms, and 100 of those terms are these problem terms. Well, what if I have 10 to the 6 states? Well, then I have 10 to the 12 terms, and I have 10 to the 6 problem terms. If you notice, the fraction of these terms that are problem terms, well, here it's like, half of the terms. Here it's 10% of the terms. Here it's 1 out of every 100 terms are problem terms. Here it's 1 out of every 1,000,000 terms are problem terms. So if you notice, the fractional amount of problem terms vanishes away. So it turns out that this Q equals Q to the n over n factorial is a really good approximation for most systems. Okay. So when is it not a good system, not a good idea? Well, let's just take a look at a few examples. Liquid helium. And this is a good approximation if the following inequality holds. So if all of this stuff multiplied together is less than 1. So for liquid helium, that stuff is 1.5. So this is a terrible approximation. But let's look at liquid nitrogen. Liquid nitrogen, 6.4 times 10 to the minus 4. Oh, it's actually pretty good. Because 6.4 times 10 to the minus 4 is a lot less than 1. Okay. So another example of where it's not a good approximation is if you look at, say, electrons in sodium metal, right, or something like that, where it favors, if you notice, it favors heavy stuff, okay? So M is downstairs, favors heavy things, so nitrogen's a lot heavier than helium. And it also favors like high temperatures, right? So liquid helium 4 Kelvin, and it's lightweight. I mean, it's just bad. If you've got gaseous helium, then you're in good shape for using this approximation. Okay. All right. So this, just as a reminder, this relates the molecular partition function, little q, to the system partition function, right? Where n is the number of molecules or atoms. And this works pretty good. You won't come across too many. I mean, if you're working on crystalline stuff, you might have the other one, but most of what we work with is stuff like gases. All right. Okay, so I want to look at one more thing on work and heat. So I want to look at the molecular interpretation of work and heat. So this comes out of chapter 19, so 19, section 6. All right, so U is equal to the summation of Pj Ej. Right, so we just kind of talked through some of this stuff, right? So this is the average energy, right? So the energy of a system can be described by that, where Pj is e to the minus beta Ej over Q, the partition function. Okay, now before we get any farther, let's remind ourselves about the first law of thermodynamics, and that is du equals dq plus dw. Okay, so what this means is a change in energy is brought about by heat transfer and work done. Okay, this is the ways that we can move energy into or out of a system. This is the macroscopic definition or understanding of energy and work and heat. So what I'm interested in doing is looking at, from a microscopic perspective, what is this differential? Well, just as a reminder, if you have something like duV, this has to follow the product rule. So this equals V du plus U dV. Okay. So when we want to do that up here to du, all right, I've got a product. I've got Pj and Ej. So I'm going to have two summations then. I'm going to have the summation of Pj dEj plus the summation of Ej dPj. Okay? So far, all we're doing is taking this, which is equation for energy from a microscopic perspective, and then we're putting in, figure out what our differential is, du. Okay? Now, if we can rewrite dEj in terms of volume. providing that n is constant. Okay, in other words, so if n is not constant, then we'd have a whole other term here. We would have partial of Ej with respect to n holding volume constant, right? That would be over here. But we're going to have a closed system, so the number of atoms or molecules doesn't leave the system. So we can substitute this in. We're going to take this guy and put him in right here. And then we're going to rewrite. Okay. Now we've got this. It looks a little complicated, but let's try to unpack what's going on here. Recall that work is like we consider the work differential dW is negative P external dV. If it's reversible work, let's make it reversible work. Oops. Then we have negative P dV. Okay. And the reason why we want to use reversible work is because that puts it in system terms, right? And all of this stuff is based on the system energies. So this is reversible work, and it's a dV term, right? It's telling us how the volume is changing. Okay. So that's this term right here. This is the work term. Well, let's see if we can understand what this means. Okay. What happens when I change the volume? So this is a change in volume. Well, this tells me the slope, right? So what happens when I change the volume? I'm moving energies. So work moves energy states by changing V. So we're changing V, and then V changes the energy states. Look back here where that work term fit in. The work term fits in right here. Changing dE, changing the energy states. dEj. Okay, so what does heat do? Well, heat is the other thing. So heat what is changing here? These are the probabilities. So, sort of schematically, you can consider this. Say you've got something like this, right? where you have your energy states. Like that. And then you're going to squeeze it, right? You're going to do work. And that moves the energy states. Instead of there, it's there. Something like that, right? Move them up. And then heat changes how the energies, or how the states are populated. Okay, so that's what heat does. It's kind of a nice picture of the molecular interpretation of work and heat. Now, what statistical mechanics is most well known for is its interpretation of entropy. And the most famous equation is that for entropy. Where S is entropy, K is Boltzmann's constant, and W, let's take a look at W. W is essentially the number of ways to have A1 systems in state 1, A2 systems in state 2, and so on. Okay, where the sum of all of these AJs is equal to A, right? So A is the total number of systems. Okay. So let's I think an example would help. Okay, so let's say that we've got a perfect crystalline substance at 0 Kelvin. Okay, so perfect crystalline substance. T equals 0 Kelvin. So, everything is in the lowest energy state, which we will assume is not degenerate, meaning there's only one state with the lowest energy. In other words, A1 equals A, and A2 equals A3 equals AN, which equals 0. So everything is in state 1. Nothing is in any other states. Okay. So W is equal to A factorial over A1 factorial times A2 factorial times, and so on, right? Well, what is 0 factorial? You may not remember this, but 0 factorial is 1. So all of these terms are 1. And so then you're left with A factorial over, and if I substitute in A1, or A for A1, W equals 1. And this makes sense. There's only one way. There's only one way to put everything in the ground state. And that is, everything has to be in the ground state. That's it. So if I calculate S, S is K, the Boltzmann's constant, times the natural log of 1, which is 0, because the natural log of 1 is 0. And this is the third law of thermodynamics, that the entropy for a pure crystalline substance is 0 at 0 Kelvin. All right, so I think we're going to stop there. I've got one more example to look at for entropy, and I'll do that in the next lecture.